So last time we looked at the derivative of the natural log, and so now let's look at integration. So before we need to do that, we need to remember what we need to look at the function natural log of the absolute value of x. So when we have an absolute value, we actually have a piecewise defined function, and we can't take the natural log of x. So we either have the option that x is negative or x is positive, not that it equals 0. When x is negative, when we take the absolute value of a negative, we are actually taking the opposite sign of the negative to make it positive. And then when x is positive, absolute value just keeps it the same. So my function, natural log of the absolute value of x, is actually a piecewise defined function. So when I take the derivative of that function, I take the derivative of the pieces. So the derivative of the natural log of negative x is 1 over negative of x times the derivative of the inner function is negative 1. To multiply fractions, let's just write that over 1. That's going to be when x is negative, and then the derivative is 1 over x whenever x is positive. So when I simplify this, I get 1 over x when x is negative, because a negative times a negative is a positive, and 1 over x when x is positive, which means that f prime of x is always 1 over x. So the derivative of the natural log of the absolute value of x is just 1 over x. So since this is the case, derivative of the natural log of the absolute value of x, when I go backwards, that is going to imply that the integral of 1 over x dx, the antiderivative, if the derivative is 1 over x, the antiderivative is the function that got me that derivative plus c. Now, we know that we can't use power rule, because if I had used power rule, what I would do is add 1 to the exponent and divide by the new exponent. We can't do that. So obviously, we can't use power rule on integrating 1 over x. And as we've already seen, the derivative of the natural log of absolute value of x is 1 over x. So going backwards is going to get me that function. So let's look at a few examples. So for this, I am going to use u substitution. So my u will be x squared plus 1, and x squared plus 1 can never equal 0, and it is always positive, because it doesn't matter what I plug in for x. When I square it, I'll get a positive if I'm dealing with the real numbers, and then add 1, it will still be positive. I suppose if I plug in 0 into x squared, I would get 0, but then when I add 1, it makes it positive. So then my du is 2x dx. So to make this 2x dx so that I can see the du in that integral, that's going to get me 1/2 the integral of 1 over u du. So now when I integrate this, I have 1/2 the natural log of the absolute value of x, or sorry, of u. Please do not forget the absolute value symbols. And then plus c, and then I substitute back in 1/2 of the natural log of the absolute value of x squared plus 1 plus c. And I do not want you to stop here. If what is inside the absolute values will always be positive, then you actually do not need the absolute value symbols. So since x squared plus 1 will always be positive, like I said before, that means I do not need the absolute value symbols. I do not know for sure if they're going to require that on the AP exam, but I will. If you can be certain what is inside the absolute value symbols will never be negative, then the absolute value symbols are unnecessary. So we want to change that out, and a statement needs to be made that as to why you got rid of the absolute value symbols. So let's look at another example. So here, if I recognize that that is the same integral as we just did, except now I'm looking at a definite integral. So I found the antiderivative was 1/2 the natural log of x squared plus 1, and that was from example 1. Now I want to evaluate this from 0 to 3, which means I want 1/2 the natural log of 3 squared plus 1 minus 1/2 the natural log of 0 squared plus 1. So this gets me 1/2 the natural log of 3 squared is 9 plus 1 is 10. And this gets me 1/2 the natural log of 1. The natural log of 1 is just 0 because e to the 0 equals 1. So that becomes 0. So I can either leave this as 1/2 the natural log of 10, or I can use properties of logs to bring the 1/2 back up, which means I get the natural log of the square root of 10. I should write this simplified. So you can either, I don't have a problem with you leaving your answer like that. Some people like to simplify their natural logs, or if the problem asks you to simplify the natural log, then that would be what it means, that using properties of logs to get it into the most compact form. But unless the directions say that, you can leave it as 1/2 natural log of 10. So let's look at this example. I'm pretty confident that your integration skills are good. So what I'm going to show you in the next couple of examples are, I don't want to say tricks because I don't want us to use tricks, but trickier problems that are going to require manipulations to be able to integrate it. So when I look at this one, I can't do u substitution because I have x squared and x squared, numerator and denominator. But what I'd like us to notice that if that x was not there, I would have x squared plus 1 over x squared plus 1. So what I'm going to do is I'm going to rewrite my integral to be two fractions, the x squared plus 1 over x squared plus 1. And then I'm going to break my fraction apart into the addition that got it there. So if I combine those two fractions, you should see that I get x squared plus x plus 1. And x squared plus 1 over x squared plus 1 reduces to 1. So now what I have is the integral of 1 dx plus the integral of x over x squared plus 1 dx. So when I integrate 1, if I do these both at the same time, I only need 1 plus c. So since we've already done this one again is example 1. So when I integrate 1 dx, I get x. And when I integrate x over x squared plus 1, I got 1/2 the natural log of x squared plus 1 plus c. If I had to do the u substitution, if I had not already found that integral, then I would wait to integrate the 1 until I was on my last step of that integration so that I only need 1 plus c. But if you want to do them separately and have two different constants of integration, that is totally fine. Let's look at example 4. So for example 4, what we're going to do is we're going to use I'm going to let u be the x plus 1 and du be dx. If we wanted to try to multiply out the denominator and use a u substitution, you're going to find that that one won't work because you would have a number there. So I'm skipping the let's try things that don't work to show you the method that we're going to go about with this. The other thing that I recognize is this does not get rid of the x in the numerator because I don't have an x dx. But what I do know is that u equals x plus 1 can be solved to be in terms of x. So now I can take my integral and substitute in for the x u minus 1 and substitute in for the x plus 1 u. So I have u squared and then dx equals du. So when I do that substitution, I'm going to distribute the integral of 2u minus 2 over u squared du. And now I can break this fraction into 2. So I have the integral of 2u over u squared du minus the integral of 2 over u squared du. And when I reduce this fraction, I now end up with the integral of 2 over u du minus the integral of 2 times u to the negative 2 du. So now I can integrate both of these at the same time. So 1 over u du, that integral is ln of the absolute value of u. So I have 2 times ln of the absolute value of u minus, when I use the power rule, I have 2 times u to the add 1 to the exponent, divide by the new exponent, and I can do plus c in 1 because I did both of these at the same time. So now I need it back in terms of absolute, or in terms of x, and this is going to be negative 2 divided by a negative 1 is a positive 2. And then I have over u, and u was x plus 1 plus c. And then I need to look, can I be certain that x plus 1 for all real numbers will never be negative? And I cannot, so I need to leave the absolute value symbol there. So for this example, we're going to use a property of logs. So I'm going to rewrite this to be the integral of 1 over, bring the exponent out front, 3x ln of x dx. And now I can do a u substitution and let ln of x be my u. So du is 1 over x dx. And what I should see here is 1 over x dx. So this ends up getting me the integral of 1/3. I'm going to move the 1/3 out front. 1/3 of 1 over u. Oopsie, I didn't change. 1 over u du, which gets me 1/3 of ln of the absolute value of u plus c. And then to put it back in terms of x, that would be the absolute value of ln of x plus c. And we can leave it there. The last one, the very last example, is how we get the antiderivative of tangent. We are going to rewrite tangent to be sine of x over cosine of x dx. If you try to let u equal sine, again, you'll get yourself in a situation where you cannot do the integration because you won't be able to see du in there. I'm going to let u equal the cosine of x. So du is going to be negative sine x dx. So to see negative sine of x dx, I need to multiply by two negatives. So now I can see negative sine of x dx in my integral. And I now have the negative of the integral of 1 over u du. So that gets me the negative of the natural log of the absolute value of cosine of x plus c. Some textbooks give this, oh, sorry, I skipped a step. Absolute value of the natural log of u, and then I have negative times the natural log of the absolute value of cosine of x plus c. I do know that some of you have, when you're doing the integration and you know you're going to have to plug back in for the u, just do that in the same step. That's fine, but I didn't want to lose anybody. Now, some textbooks give this as the antiderivative of tangent of x, and some books give another version, and I want to show you how they get that version. I have my negative out front, which using power or using rules of exponents, that means I want cosine of x to the negative 1. This is not inverse cosine. This is the reciprocal of cosine. Notice I did not put it on the cosine function. This is 1 over the cosine function, not going from a ratio to back to an angle. So now what I get when I do the reciprocal, I get 1 over cosine of x inside the absolute value, which is the absolute value of secant x plus c. So depending on the textbook, there are some textbooks that use this for your antiderivative of tangent and others that use this, but they are still the same antiderivative. So let's review our antiderivatives of trig functions. So the trig integrals here, we already know the integral of sine of x dx is negative cosine of x plus c, and we know the integral of cosine x, and we now know the integral of tangent of x. It's either that form or the other form. Cotangent of x should not surprise you that it is in a similar form to tangent of x, and then the integral of secant x dx and the integral of cosecant x dx you can see there. I believe the book derives them. You are not expected to have these two memorized. These would be ones that if it showed up on an assignment, you knew where to look to find what that antiderivative was. You would not have to solve it or do the integration. And if it did show up on a test, it would be on a take-home test, not an in-class test, so that you could find that integral and not have to know it from memory.